incoherence. Okay, and so today's talk is going to be about fibering. So yesterday I used homology to give a sort of I gave you all of the details of an example of an incoherent group and then told you where you can embed that. And then at the end, there was a question about whether this was sort of the industry, whether, you know, proof coherence was basically like embed a direct product of free groups and then you're done. And that works a lot of the time, but it's not going to work all the time. And so today I want to talk about some places where that doesn't work. So, okay, so I want to talk about fibering. So I'll get to the definition of fibering in a minute, but first let me start with another sort of thing about classifying spaces. So in today's talk, I'm going to be interested in groups of type F. Okay, so a group is of type F if it has a classifying space with finitely many cells. Okay, so yesterday we talked about finitely presented groups, and I said that a group is finitely presented if it has a classifying space with finitely many 0, 1, and 2 cells. Okay, and so now I'm just requesting finitely many cells. Okay, so in particular, this is a finite dimensional CW complex. Okay, and so some examples are, some examples we've seen already are free groups. The classifying space is, the classifying space is a wedge of copies of S1. Radhika talked about this, and this came up earlier today. Surface groups, the classifying space is surface groups. So let's say not RP2. Okay, and as long as you're not RP2, then your surface is actually a classifying space. Okay, the universal cover is contractible. It's either, it's homeomorphic to the Euclidean plane. So, what else did I say? Free abelian groups. You have the obvious thing here. So X is just a product of copies of S1. And this is a classifying space. And the last thing that I want to mention is torsion-free hyperbolic groups. Okay, so this is this uses what's known as the Rips or the Rips for torus complex. Okay, and so you can prove that torsion-free hyperbolic group has exactly this. It has a classifying space with finitely many cells. I guess equivalently, some people just to say that this is another way of stating this is maybe here you could just say that it has a compact classifying space, right? And that's equivalent, right? A CW complex is compact if and only if it has finitely many cells. So, okay, some non-examples. So one thing that you should notice that, I've said torsion-free hyperbolic groups and I've ruled out RP2. So actually the reason I've done that is because groups with torsion never have this property, which is a little bit sad. So any group with torsion requires an infinite dimensional classifying space. Requires a classifying space with infinitely many cells, and those cells have to have unbounded dimension. If you want a torsion-free example, then the easiest, what am I going to say, the easiest example I know? If you want a torsion-free example, then something that's sort of been mentioned this week is Thompson's group F. Okay, so Thompson's group F is a torsion-free group. It has no compact classifying space. And in fact, it has the similar properties to torsion groups. Any classifying space has cells of unbounded dimension. Okay, so you could also have other failures. So not finitely presented groups, right? So type F is like some sort of stronger version of finitely presented. And exactly this first part of this proposition is that if a group is type F, then it's finitely presented, right? If you have a classifying space with finitely many cells, then you have a classifying space with finite 2 skeleton. Is there a question in the chat? I didn't put the chat up.
Yeah, we're wondering if there's a good reason why torsion kills the possibility of a compact classifying space.
So yeah, give me one more slide and then I will explain. It's not it's not maybe the easiest reason to see, but I will be able to tell you why. Okay, so type F implies finitely presented, right? If you have a yeah, exactly what Jesus is saying, that this is going to be what comes up in some sense. If you have finitely many cells, then you have finitely many 1 and 2 cells. It's preserved by passing to subgroups of finite index. Okay, so this is in some sense, this is pretty. In some sense, this is really just this is an easy covering space argument. Okay, you just take the covering space and finite covers of finite complexes of finite complexes. A harder thing that I'm not going to prove is that if N and Q are type F and G fits into a short exact sequence, N goes to G, goes to Q, okay, then G is type F. And you can sort of think about how you build if you sort of know anything about fiber bundles, then you can maybe build a classifying space for G as sort of a fiber bundle of the classifying space for N over the classifying space for Q. It's very vague, and right, I want to say, I've written in my notes a little thing that says that this is harder. So that this is harder to prove, okay, but you can think about it. And on the exercises, I've given you an exercise to prove that this is true if you replace type F with finitely generated or by finitely presented. And for that, you can actually sit down and really see what the 1 and 2 skeleton should be. Okay, so these 2 facts are going to be useful later. It's I don't think the sequence being split really helps you. I don't think it really helps you. I think that you still end up having to sort of do some fiber bundle construction, which is kind of a little bit non-trivial to do. So it's preserved under finite index, and it's preserved under, you know, short exact. It's preserved under extensions as long as both the kernel and the quotient have type F. And so another consequence of type F is that it tells you something about homology. So, so an observation is that if G is type F, then HI of G is finitely generated for all I and 0. So HI of G is isomorphic to Z to the Ri direct sum torsion, right? This is sort of the classification of finitely generated abelian groups, and actually, so, and HI of G equals let's say it like this. So another thing that you can observe is that there exists N such that H J of G is 0 for all J greater than N, right? Your classifying space has finitely many cells. In particular, it has bounded dimension, and so your homology is going to vanish after that dimension. Okay, and this so this is an unsatisfactory answer to the question that I postponed. But if you have a finite group, then it turns out that if you have a finite subgroup, then it turns out that this condition will fail. Okay, so it turns out that if you have a torsion subgroup, then you're going to have homology in all dimensions. Okay, and so that tells you. So once again, homology is really the reason why you can prove these things. Okay, so so if G is of type F, then homology is of this form, right? It's a finitely generated group, and this allows us to define the Euler characteristic. I'm immediately realizing that I should have just said that. Okay, well, the Euler characteristic is so you just define it in the same way you do for any topological space, right? It's just the alternating sum of the ranks of the homology groups. Okay, so you know, people have different definitions of Euler characteristics. So this is the one that I'm sticking with. It's the alternating sum of ranks of homology groups. And so some examples that you can sort of quickly compute: the Euler characteristic of Fn is 1 minus n. Okay, your classifying space has one vertex and n edges. So, so you can just compute the homology. So this is, so I guess I should have said that this is equal to the Euler characteristic of a classifying space. Right. So the Euler characteristic of the fundamental group of a surface, right? It's just the Euler characteristic of a surface, which for an orientable closed surface is 2 minus 2g. The Euler characteristic of z to the n is 0, and you can check. So if you, so today apparently I've decided that I'm going to use F2 for the free group of rank 2. You can check that the Euler characteristic of a product of two free groups is 1. The product of two rank 2 free groups. Okay, so we'll see what it is more generally in a second. Okay, so and you can do this by just building. You can just build a classifying space and compute the homology, or you can just count the cells. Okay, so it turns out the Euler characteristic is going to be sort of a key invariant, and actually, when I come to open questions tomorrow, we're going to see it come up again. Okay, so so it's kind of amazing that it's a rather basic notion, you know, but it actually tells you quite a lot. And so some sort of observations or theorems. So if you have three groups of type F, then firstly, right, if you take a finite index subgroup, then the Euler characteristic just goes up multiplicatively by the index. Oh yeah, that's a great point. Sorry, so the Euler characteristic of G, so you need G to be, that's a great point. Type F, right? So the Euler characteristic is perhaps defined more generally, but for us, we're going to define it as type F. Okay, because exactly the point that's being made, I want this sum to really be a finite sum. Thank you. So, okay, so firstly, it goes up multiplicatively with the index, right? And you can prove this quite quickly for just using covering space theory. Another thing which is harder is that if G, so similarly fits into a short exact sequence Q, G, N. So same as before when I was talking about type F, the group in the middle is of type F, and the Euler characteristic is just the product of the two Euler characteristics. Okay, and this is non-trivial to prove. Okay, so so there's a very short anecdote about me when I was a grad student. You know, I came across things like this, and my supervisor would tell me, well, if you want to prove this, it's just an easy spectral sequences argument. And I would sit there and say, well, what is an easy spectral sequences argument? Because spectral sequences seem impenetrable. And now I'm 4 years out of grad school, and I was writing this talk, and I thought, oh, that's just an easy spectral sequences argument. And then I realized that it's happened. So so this uses spectral sequences, and it's I will happily talk to you about it. It's really not that hard. You just have to understand a very small amount of homological algebra. But right now, I'm going to gloss over it. Okay. So, but the point being that, right, if you know the Euler characteristics of the kernel, then you can recover the Euler characteristic of the group in the middle, and it's just true for it's true for spectral sequence reasons. So, okay, so this is going to be this is really going to be useful. Okay, so right, so now I've defined the Euler characteristic. I want to talk about how we're going to use the Euler characteristic. And what we're going to do is we're going to sort of use this with fibering. Okay, so what does fibering mean? So maybe I said the word fiber bundle earlier, and maybe for those of you who have maybe some background in manifolds, or you've thought about three manifold topology, as a lot of people in geometric group theory have, maybe you have some idea of what fibering means topologically. On the group theory side, I'm just going to mean that we say G fibers if there exists some map phi from G onto Z such that the kernel of phi is finitely generated. Finitely generated. Okay, and this, right, so this double arrow by, I mean surjection. This has probably been used already, but okay, and so an easy proposition is that, so as I say, fibering has sort of been something that's come up a lot, and I want to talk to you in a minute about a really great theorem about fibering. But first, you know, a sort of proposition or just an easy observation is that if G fibers and the Euler characteristic of G is not equal to 0, then the kernel of phi is not of type F, right? Because if it were, right, so the proof is that if the kernel of phi is type F, then the Euler characteristic of G is defined. Okay, G is of type F. It fits into the short exact sequence. The Euler characteristic is just the product of the Euler characteristics. So let me call this K. So it's just the Euler characteristic of K times the Euler characteristic of Z, right? But we already said that the Euler characteristic of a free abelian group is 0. So, well, let's say that this is the Euler characteristic of K times 0, right, which is equal to 0, but we've assumed, you know, by assumption, the Euler characteristic of G was non-zero. So the second you have something with non-zero Euler characteristic, you're actually in a really good position. Like, you already know you have this finitely generated kernel. You know it's not of type F, and so somehow, not finitely presented implies not type F. There is a middle ground there, but maybe you could bring this down. Okay, and there are theorems that that really do this.
Rob, do hyperbolic three manifolds have Euler characteristic 0 always then?
Yeah. So
oh, that's so weird.
So actually, you know, this closed three manifolds, closed three manifold implies the Euler characteristic of M equals 0. This follows from, just to say the words, this follows from the Haygot splitting. You can compute the Euler characteristic from the Haygot splitting. So in fact, the Euler characteristic of a three manifold is controlled by the Euler characteristic of its boundary. That's a very cool fact. The question was, do hyperbolic three manifolds have Euler characteristic 0? Riley's using the extra fact that she knows that they fiber. And so, and in fact, in that case, the kernel is of type F. And so she's using the contrapositive of this theorem proposition. Let me skip my next two slides. Well, what do I want to do? Let me come back to them if there's time at the end. Let me for now just skip them. I wanted to give you a criterion for virtual fibering, but yeah, I'll come back to it. Okay, so how can virtual fibering be used? Right? We have this middle ground. We know that the kernel's not of type F, and so maybe we could bring this down to saying actually it not being of type F is seen by the fact that it's not even finitely presented. And this is sort of exactly what this is a tool that I want to tell you is great for proving that things are incoherent, is a theorem of Bieri from 76, which says, so let G be a group with a two-dimensional classifying space okay, so right, so two-dimensional classifying space is quite a strong condition, but there are a lot of interesting groups that fit this theorem, and I'll give you some examples in a minute. So Bieri says that if you have a normal subgroup of G, that is finitely presented, then either it's finite index. Okay, so either it's just a finite index subgroup, you've just passed to a finite color, or it's a free group. Okay, so you're in this dichotomy. The second you know it's finitely presented, you know that either it's finite index or it's free. And so this tells you that, so if G is as above, fibers, what did I say? Oh, if G as above, the Euler characteristic of G is non-zero and G fibers, then G is incoherent, right? I mean, the proof is, there's not really that much to say. Okay, so you have this map phi from G onto Z, K equals the kernel of phi. If K, so this is K is finitely generated, right, by the assumption that it fibers. If K finitely presented, then the Euler characteristic of G, it's the same thing as before. Then K is free. Implies type F, implies the Euler characteristic of G is equal to 0. Okay, so it's the same as before. And you can actually say even more about. So it turns out that that you can actually say something about the quotient. So if N is a normal subgroup of G, which is finitely presented, then the quotient is a virtually free group. So it turns out that you don't even, these things don't. There aren't that many quotients you can get.
We have a question in the chat that asks you, like, what goes into the proof of this Bieri's theorem?
Oh, yeah. So I was trying to spend a little bit of time understanding this and really quite failed. So I think what goes into this is a certain amount of homological algebra, and because I believe that the Bieri's theorem is correctly stated as using type FP2, but I might be telling a lie. So the answer is I don't really know off the top of my head.
Could you get a stronger result that says that actually G, if it has Euler characteristic 0, is like virtually free-by-cyclic or something like this?
I think you can. I think if you combine.
Oh, I guess you've kind of written it down. Yeah, if K is finitely presented, then it's free. And the Euler characteristic is 0, then
if you just have to worry that even if the Euler characteristic 0, you might have a finitely generated, not finitely presented subgroup. Something. I think you can. I think you can get it with other theorems of Bieri actually, and actually that I'm nervous that I have to say the word hyperbolic somewhere. So yeah. You can't really say anything about non-normal subgroups, just to answer a question in the chat. So there's a question in the chat about whether you could say anything about non-normal subgroups. It turns out that you really need to use normality. Groups with two-dimensional classifying spaces can be quite strange in many ways that I will happily talk about more, but not right now. Any other questions about Bieri's theorem? Okay, so so this is a great theorem. This, why do I think that this theorem is worth telling you about? I mean, it's 44 years old. That might, theorems don't go bad. And actually, I've used this, so I think this is an amazing theorem. I think this is a really great theorem to prove that things are incoherent. And I wanted to tell you 2 results of mine. Oh no, I don't. No, first I want to give you an easy application. Perfect. My slides are off on my computer. Why didn't I just look at them? you can actually use this to easily prove that F2 times F2 is incoherent. So yesterday, I carefully constructed this not finitely presented subgroup, and then I embedded it in F2 times F2. And I sort of alluded to the fact that it was the kernel of a map to Z. And I alluded that it was this map, right? Or I said that it was this map. And so you can check that here is a map from the product of two free groups to the integers, right? You take all of the generators and you send them to 1. And you can check that the kernel of this map is generated by this set. Okay, it's not particularly hard to see. The point is that this is an exercise basically, but the point is that because the s's and the x's and the s's and the y's commute, you can take these powers and then you can just use the same proofs that I told you to use for free groups. So I think the thing to do is show that these these, if you replace the ones with n's, then this generates. That's really quite easy. And then use this fact to show that these 4 generators suffice. Actually, 3 of them suffice. Okay, so I've got this kernel. The Euler characteristic of F2 times F2, I've already told you, is equal to 1. So K is not finitely presented, right? So this is just a completely different proof, right? It just uses Bieri's theorem by Bieri. Okay, right? You just the second thing, Euler characteristic's non-zero. You have this map to Z. You have finitely generated kernel. You're done. It's all over. And so an exercise is so the exercise I wanted to give you here was so you can do the same thing. Show the same result for the right-angled Artin group on an n cycle. Okay, so this is the group, just to write it down, this is the group generated by n elements such that AI commutes with AI plus 1 and A1 commutes with AN. Okay, and so the thing to do is there's a map. So this maps to the integers where you just send all the AIs to 1. So firstly, show that this kernel is finitely generated. And there's sort of a similar trick here where here really here are the, right? So you can see F2 times F2 as the case when n equals 4. And here's the sort of correspondence between those generators. And so sort of generalize this trick to show that the kernel of this map is finitely generated, and then compute the Euler characteristic. So the Euler characteristic of this guy, right? Compute the Euler characteristic. I think it has Euler characteristic 1. But you can compute it, and maybe I don't know, depending how. Yeah, we can talk about this in office hours if you like. Right, so this allows you sort of very quick proofs. And so, okay, so I actually use this in two sort of quite recent theorems. So firstly, we managed to, it turns out that if you have a free-by-free group, so a group that fits into a short exact sequence where the kernel and the quotient are free, then these groups have a 2-dimensional classifying space. And as long as they're both non-abelian free groups, then these things are incoherent. And what did we do? I mean, in the end, we proved it in a different way, so this might not be written down in the paper, but our initial thought or our initial strategy was show that these things fiber. And when they fiber, we can use Bieri's theorem. So then the hard part, we shifted the hard part from showing something's not finitely presented to showing something fibers. And then we did a similar thing in a paper with David Kielak and Gareth Wilkes, where we showed that if you take a random 2-generator group, which has at least 2 relations, so things are incoherent asymptotically almost surely. Okay, and we did a similar thing, right? It turns out that these groups have two-dimensional classifying spaces, and so the real thing we did was prove that they virtually fiber, and incoherence followed as a corollary of that. So telling you about those theorems, I think that I'd happily tell you, I'll happily talk more about those theorems, and possibly some of you have seen me or Gareth give a talk about of these theorems. But what I want to tell you about is the theorem of Rips, which I think is great, which is a great thing to have in your toolbox as a geometric group theorist. So Rips's theorem said that there exists incoherent hyperbolic groups. Okay, so last time we saw this example of F2 times F2. On the previous slide, I told you could do this for right-angled arting groups, but those are always going to contain z squared, so they're never going to be hyperbolic. Now, it turns out that you can get hyperbolic examples here, and these examples are hyperbolic, but they're not very easy to write down specific hyperbolic examples. But Rips actually allowed you to write down a very specific example. And so I want to tell you how you prove Rips's theorem. I'll give you an outline. Let me pause for a second. So very specifically, what I want to do is I want to give you a concrete example of an incoherent hyperbolic group and the method with which Rips showed that incoherent groups exist. And then Rips's actual theorem is an exercise, and it's not a hard exercise, but I think it's one that's really worth going away and doing because it really shows you the power of things like small cancellation theory and Rips's original construction. And just playing around with those things, I think is a great tool to have. At least it's one that I constantly use. Okay, so Rips's example. Let's talk about Rips's example. So, okay, so if we have a presentation XR, then we say that P is a piece. So this is going to be a word in the free group on X. If, now this definition is going to seem completely opaque, so just bear with me. So if there exist relations R and S in R such that there exist cyclic permutations R prime, there exist cyclic permutations which aren't equal as words in the free group of R plus minus 1, S plus minus 1, such that the first one is your piece P followed by some word U, and your second one is your piece P followed by some word V. Okay, so this definition has sort of a lot of algebra, and right, I wanted to give it to you so that I don't tell you a lie. Okay, now the following definition you have to make rigorous, but it's much more enlightening, at least in my opinion. So geometrically, what does this mean? What this means is that in the Cayley graph, so in the Cayley graph of G, with respect to the generating set X, we see the following picture. So we have our word P, right? And if we continue reading P, then we can get to some loop R, right? And what does this cyclic permutation really mean? The cyclic permutation just means that you didn't start your loop here. Maybe your word R started at some other point. You've just forgotten where it started. Okay, and you also see on the other side some word S. You see this word S. Okay, so what it means is that in the Cayley graph, this piece P is sort of a subword of two relations that meet along this piece P. Okay, and this point about the cyclic conjugates being not equal is you don't want to have just taken R twice, right? That would be sort of the silly thing you could do. Okay, so this is about, so a piece is basically the overlap of two relations. And you should really think of your relations as words on circles, and you should forget that they have a base point. Okay, so this is what this cyclic permutation means. It just means that your circle doesn't really have a given start point. Okay, so yes, so this is what a piece is. And so you can use this to define small cancellation conditions. So we say that a presentation satisfies C prime lambda if whenever P is a piece of R and S, then the size of P is less than lambda times the size of R. Yeah, okay, so, right, so this is saying that pieces are somehow small proportions of words. They're sort of, if you have a relation, then the overlap between two relations, okay, this part here is, you know, at most lambda times this length here, okay, and this definition is symmetric, so you could also say less than lambda times x. And so as an example, you know, this was actually, this goes back, I guess I want to be slightly careful about my history, but, you know, sort of the easiest example is a surface group with its standard presentation, right? So if you take this surface group, okay, then if you look at the overlap of two relations in the Cayley graph, okay, so you're allowed the same relation, you're just not allowed the same cyclic starting point. So the pieces that you can get are A plus minus 1, B plus minus 1, C plus minus 1, and D plus minus 1. Right, so you can check that these are the only pieces you get. If you just think about, how octagons tessellate the hyperbolic plane, you'll see that two octagons share a single edge in the usual tessellation. So these are the pieces, and it has one relation of length 8. So this is C prime lambda for all lambda greater than 1/8. Okay, each piece has length, you know, it has length less than 1/7 of the relator. Okay, and you can't take 1/8 because this is a strict inequality. Okay, you know, a slightly more hand wavy example is the following. So I wrote down one more example. So same set of generators, and let's take as my words. Oh, why did I do this to myself? Okay. Oh, I see. Right. So it's pretty easy to come up with small cancellation groups. You just pick words that have very little overlap with them. A5, B5. Okay, so this is also a one group, right? And so what's the point? It has one very long relator. So the length of this relator, is, I decided it was 70 earlier. Okay, so I mean, if you, right, there's 10 coming from here, and then this is 4, 8, 12, 16, 20. And I think those numbers add to 70, but, you know, much like Federico, sometimes I'm liable to make mistakes given things like this. Okay, so the length of the relator is 70. Now that there are a lot of pieces, so let me just write down a few. So pieces. So one piece that appears in two places is this C to the 4. Okay, so there's sort of your first piece. Oh, yeah, sorry, I should pause for a second and say that really the point of a piece is it's a word that appears in two places of a relation, or it appears in the inverse. And the only reason why I went to this whole trouble of saying cyclic permutations and drawing this picture in the Kielak graph is that you're also allowed things that sort of start at the end and carry on at the beginning. Like you're allowed things that sort of wrap around the end. So you're really just looking at, so pieces are really just subwords of relations. So this piece, c to the 4, appears twice. Another piece that appears twice is d. Okay, so d appears here, and in the inverse of this relation, this becomes a d. Okay, so you have two of them. You know, you end up having, so there's sort of an AB in this commutator, and then there's an AB in this commutator. There are a lot. The largest piece, so you should check this, but sort of the largest piece is a to the 5, b to the 5. Okay, and so, oh no, the largest piece is a to the 4, b to the 4. Okay, so you should think about why this is the largest piece that appears, but this a to the 4, b to the 4 appears in this commutator and it appears in this commutator. And then you can't get anything larger. You can't, you know, the second you start adding in extra a's, it's not going to appear here. You start adding in extra b's, it's not going to appear here. And then if you start adding in c's and d's, you can quite quickly see that it's not going to appear anywhere. Okay, and so this is c prime, anything bigger than 8/70. Say c prime 1/7. Okay, or you know, c prime lambda larger than 8/70. Okay, the point is, so the point I'm trying to make, and I'm sort of obscuring this by writing down a very specific example, is it's quite easy to come up with small cancellation words. You just start writing down things that don't overlap, and you end up with a small cancellation very, very quickly. Okay, and this sort of trick, this sort of commutator thing, I mean, commutators are great because it turns out that the two commutators don't have that much overlap, right? This is sort of the trick that I'm using, and this is a trick that I'm going to use in a second. Okay, so so everyone's sort of happy with the idea of small cancellation theory. I could see sort of out the corner of my eye that lots of things were popping up in the chat, but it looks like combinations of people are answering the questions. So, so yeah, the idea is you want things with small overlap, and these things are very, very easy to create. And here is sort of a method for creating them, right? This is what I'm gonna, right. This commutator thing is a method. Oh, great. They're on my computer. Why do I do this to myself? So why do we care about small cancellation theory? Why c prime lambda? Well, it turns out that c prime lambda is a great condition. It gives you a lot of consequences. So if lambda is less than or equal to a sixth, and g is c prime lambda, and no relation is a proper power. So this is, you can have relations that are proper powers, and they just cause a minor amount of annoyance. So I'm just going to royal them out. So in that case, g is torsion free, right? So basically, this this condition over here, if you have a c prime 1/6 group, then any element of finite order, you can actually see a relation of finite order, right? You can see a relation which is a proper power. So the second you, I forgot the word no, such that no. The second you have a finite order element, you can see a relation which is a proper power, okay? And just to say that this means that r equals w to the n for some n greater than 1. So as long as you don't have any proper powers, then you're torsion free. In fact, you're torsion free hyperbolic. Okay, so you're type F. Even stronger than that. In fact, the Cayley 2 complex is a classifying space. Okay, so if you build the complex which just has one vertex, a loop for each generator, and then you glue on a 2-cell for each relation, it turns out that in that case, this is a classifying space. You don't have to do anything more. You're done there. And so you can see from this that the Euler characteristic is exactly 1 minus the size of x plus the size of r. Okay, and we actually know even more now. So so sort of, this is right. So this is all quite classical. This is all in Linden and Shup's book on combinatorial group theory. But small cancellation theory has sort of grown from that. And I'm going to put some references to there are sort of more intricate small cancellation conditions, and you can use it in more places. For instance, a notable, interesting recent application has been to Burnside groups, but there are sort of many applications. And one thing that we now know is that, after Agel and Wise, we actually know that these things are virtually special. And so in particular, they're residually finite. Okay, so actually, Agel, so Wise showed that these things were cubical, and then, after sort of all of the work of Agel and Wise, you now know that hyperbolic cubical groups are virtually special, and so you get sort of a real amazing list of consequences. Okay, so this is why you might care about C'(1)6). Okay, so it really lets you know something very, very nice about your group. Okay, so the thing is that it's a great tool. It's very flexible because you can just start writing down words, and then you very quickly find out that you've written down some small cancellation word, and so you can use it to construct hyperbolic groups. You can construct interesting examples. Okay, and so here's one specific. So I'm just going to do one specific example, but you can generalize this example. Okay, so let X be the set AB, and I'm going to take R. So let K be an integer. For reasons that will become clear in a second, just take K larger than 48. Okay, let Wi. So Wi is going to be, I'm going to do a similar thing with commutators, right? This is my, I'm writing a paper with Riley and Thomas, who are both here in the chat, and somehow they probably know that I just love commutator tricks. So and you can really do a lot with commutators. Okay, so let Wi be the word A to the ik plus 1 be sort of this product of commutators. Let's write out the next one. Ik plus 2, b to the ik plus 2, all the way up to a to the I plus 1, k, b to the I plus 1, k. Okay, and let R equal, sorry, let's just say, yeah, let's let R equal W1, W2, W3, W4. Okay, so I've taken 4 words, okay, and they're just products of longer and longer commutators, okay? And so we can now compute the length of these things. Okay, so this is this is an exercise, but so the length of, if you look at the length of Wi, then the length of Wi is at least the length of W1, and if you look at the length of W1, I claim that this is for I, as I ranges from 1 to k. Okay, and if I manage to write down if I believe the geometric series I've written down earlier, which I'm not sure I do, then this is at least this, which is greater than k squared. Is that what I said? Okay, so the point is that these words have length sort of bounded below by k squared. They're at least as long as k squared. What are pieces? Well, you know, if you look at pieces, you can see a lot of pieces occurring. So for instance, AB is going to appear in sort of all of these commutators. It's going to appear in all the commutators of these words. But if you look at pieces of maximal size, then what you'll find out is that basically a piece of maximal size is have length. So basically the maximal size piece, it turns out, will be in W4. Sorry, it will be the last thing in W3 and the first thing in W4. Okay. And so you should convince yourself of this. So pieces of maximal size have length less than or equal to, say, 8k. Okay, whatever. Like, don't worry too much, but you should sit down and you should look at these words and you should convince yourself that, you know, pieces are basically linear. You're not going to have a piece which goes between two commutators. And so any piece is going to have length less than, say, than 4k. Any piece is going to have length less than 16k. Okay, it's pretty easy to convince yourself of that, and you can do a little bit better. You can probably do slightly better than 8k. But the point being, okay, so if you compare the sort of length of pieces to the length of words, they're very, very small. Okay, this, you know, calculus 1 tells you that 8k over k squared goes to 0 as k goes to infinity. And so it turns out that this condition I said here, where k is greater than 48, so k greater than 48 implies that this presentation is C prime 1 over 6. Okay, that's going to be the consequence I use. That's all I'm going to use. Okay. Yeah. So as long as you do these, right, and you can just do larger and larger commutators. You can make this C prime 1 over 1,000 by just taking these commutators large enough. Okay, so this commutator thing is allowing you to put in very, very long words with very, very small overlap, which is going to be helpful for one of the exercises that I've suggested. And the exercise I've suggested is how to prove Rips's actual theorem. Okay, so what am I going to do with this? Right, well, I said this allows me to construct hyperbolic groups, and that's exactly what I want to do. So let's build sort of Rips's example, or an example of Rips's type. So we're going to let Wi be as before. So I've written down these. I've written it down here, and I'm going to let G be generated by 3 generators, and I'm going to give it 4 relations: W1, W2, W3, W4, and A, B, T inverse, T inverse. Okay, and so these relations are, if you conjugate A by T, then you get W1. If you conjugate B by T, you get W2. If you conjugate A by T inverse, you get W3. And if you conjugate B by T inverse, you get W4. Okay, and so the point is that, okay, so now you look at this presentation. And what I'm going to say to you is that there are extra pieces, but they're very short. So the extra pieces, there's like these T pieces, but they have length 1. So you're not, like, the size of the piece hasn't really changed. So this is still, C prime 1/6. Okay. Now the great thing is that that this presentation, so the reason for these conjugation relations is really to force AB to be a normal subgroup. Okay, so I've written this presentation out again here. And so we can define phi from G to Z, which takes A, B, and T. I mean, you could compute the abelianization, and this is really the only map to Z, but here is A map to Z. Okay, you send A and B to 0, and you send T to 1. You can check that all of these relations hold, right? I mean, the W's are products of commutators, so these are going to vanish in an abelian group, and these T's are going to cancel out. And so, right? So this is a map. It's a surjection, so that's good, right? What's the kernel? Well, the kernel, it's not too hard to see that the kernel of phi is the normal closure of A and B, right? If I take all products of conjugates of A and B, then that's going to be the kernel of phi. But actually, the reason for these relations is that, A comma B is a normal subgroup of G, right? Why did I construct these relations? I constructed them so that it's a normal subgroup, right? If I conjugate A by A, I get A. If I conjugate A by B, I get some word in A and B. And if I conjugate A by T, this relation is saying, well, you actually get a word in A and B. And similarly for these four, right? You're going to conjugate things by T, and you're going to remain in the subgroup generated by A and B. So actually, the kernel of phi, right, is equal to AB, right? Hence G fibers. Hence G fibers. Now, you know, I said that G is two-dimensional. Its Euler characteristic is 1 minus 3 plus 4, right? And so actually, this kernel can't be finitely presented. So A comma B is not finitely presented. Okay, and so there you go, right? You've just, this is just constructed a very explicit example, where you can actually write it down. You can write down, right? There was a discussion before this lecture about how, you know, if you look at the monster group, you can actually write it down. It's a finite group. This isn't just that there exists a hyperbolic group, which is incoherent. I've actually written it down for you. Okay, and I've even written down what the subgroup is. Okay, and you now know this kernel isn't finitely presented. And so in general, so Rips showed something. Rips showed something much more than this. Rips actually showed that given any, that you can actually replace Z here with any finitely presented group, and you sort of do the same thing. You have extra relations, and you make these words longer to compensate for your extra relations. Okay, and I've sort of outlined this on a problem sheet, and I think that it's worth, and as I say, it's worth sitting down and actually doing these computations once, because the thing is that if you actually write down how to prove Rips's theorem, right? If you actually write down what these small cancellation words are and how this is all going to work, you suddenly realize the freedom you have in writing down small cancellation words. And then suddenly when people ask you questions like, can you construct a hyperbolic group with such and such a property? Or, you know, somebody recently asked me, can you construct a two-generated hyperbolic group that isn't free? Well, it's quite easy. You just write down a small cancellation group and you can make it have trivial first homology or something. Like you can just start writing down easy examples of hyperbolic groups using small cancellation theory. Okay, so that's all I wanted to say today. Thank you all very much for listening.